Hey, there we go. That worked that time. Um, I know. I promised I'd be doing more engineering. We'll get there. But I was consuming, as it were, some interesting uh, sort of digital creator software engineering content the other day, and this one guy who I won't say exactly who does do pretty interesting stuff. Can be a little bit iconoclastic. Um, Went on this weird rant about how obscure, obtuse, and inaccessible OpenGL is. It was very strange because the critique was based on how difficult it was to get something in pixels, just like sprites and pixels up on the screen. And there are many things to complain about with OpenGL, but compared to like pretty much every other, compared to DirectX to a degree, compared to Vulkan, compared to like, there's a lot of things you can complain about OpenGL, but like it's pretty well established. It's pretty straightforward to get up and going. And this guy's pretty experienced. He's skilled. He knows what he's doing. So the comment was strange. It seemed like it came in a number. So it got me going and trying to think like, okay, what is the simplest, shortest path for someone with a completely fresh project to get up and going with? Just like you want to create animation, or you're going to create a small game or something, like you just want to put sprites on the screen, right? Like, what is the shortest path to do that? And unless you're using something platform specific, like I don't know, old school Windows GDI or whatever, like GL's a really good way to go. There's a few other things you need in combination with it. SDL is an absolutely fantastic library. It's strongly recommended. I haven't checked it out, and there's a lot more to it, but it is for getting like out of the box and going with a window and event loop and a geo context and all that is fantastic. And of course, glue is practically required for a lot of things. So what we're going to do today is walk through. This should be fairly quick. A very brief demonstration of just sort of what the shortest path to working, not necessarily MVP, but working sprites on screen is. So let's start with a basic C++ project. We're going to use CMakes for this. I'm not going to, and let's, what do we call this, 11? Okay, so what do we need first? First, we're going to use submodules to manage our dependencies. This turns out to be pretty straightforward. I mentioned SDL. Let's go ahead and use that. GL itself as a library is probably already installed in your system, in most modern systems, so that's not really something you need to worry about, like reaching out and fetching as a package. So let's see. Submodule add from, this is from a specific branch if I remember correctly, SDL2. That should do it. Okay. The other thing I want to include here is SDL image. It's technically not required, but if you're not using it, then you're like manually doing either raw bitmap loading or you're like splicing surfaces and splitting surfaces. And you don't really want to do that directly if you're just trying to get a sprite in. SDL image is one of many, many extensions to SDL. Others, SDL thread, SDL type, etc. But SDL image is fantastic because it's self-contained, includable as a module, and gives you almost instant access to many different image file formats that you may need to worry about juggling. So let's add STL image here. Again, we're going to use a submodule to hook it in. We're going to want a specific branch. I believe that was also an SDL2 branch. And then since it's a one-way consumable, we'll just do null. And then lastly, I mentioned glue. Glue is fantastic, but we do need a version of glue, since we're using CMake to bind all this together, that supports inclusion by CMake. So there are branches of that, or forks, that are very useful. Wait for this to finish. 98, 99. And this is the last one, I promise. So I don't think this is from a specific branch. I think we can just say BAM. Okay, and that should be pretty quick. All right, so we have our submodules. Let's initialize them. I believe there's some recursive dependencies in SDL image. This might take a few moments, but that's okay. And then let's start walking through some things. The CMake project, so we don't really want to include our build artifacts. We're going to have a set of submodules here that we've loaded from the command line. We're going to have some sort of main program here, of course, with our C++ code. I also want to be able to demonstrate, and this is actually incredibly useful, some GLSL. So this is not technically required, but if you start out thinking of your sprites as basically two-dimensional, fragment sets that need to have a specific graphics pipeline, that gives you a nice incremental way to expand to it, even if you're just doing a 2D game. A lot of really interesting effects and a lot of different interesting ways to manage like the transform and displacement and movement and relationship of all of those sprites, including like depth management as well. So we're going to include some shaders here. If you haven't messed with GLSL before, it's fascinating. I'll probably do a specific talk at some point on radiometry and its relevance to engineering and computer programming. And then just to, we need a logo of some kind. What should we use for logo? Oh gosh. Don't ask me why, but here is a nice picture of a seagull. Isn't that a wonderful seagull? Yes, it is. Let's just drop this in here. Let's just say logo PNG. All right, so our goal, our mission, if we choose to accept it, is to put that up in a window. If we do this well enough, it'll be fairly clear how to move forward in the future with something a little more sophisticated, but this should be enough. So let's take a look at CA submodules are finished. Let's go ahead and make sure those submodules are being tracked now. Okay. Boop. There we go. See our submodules here, and now we can start coding. Okay, where should we start? Let's start in main with some dependencies. We're going to need files, manage some files, some stream reporting, some stream management for juggling shader, content, and paths and all that. We're going to be representing data structures in vector format. We're going to need STL itself. Let's assume that will be put on an include path by the CMake configuration, and then our dependencies. So STL will come from STL. GL glue is, if you look in the include path here, it's all under GL. And STL image has just sort of a single entry point header here. Okay, so let's take a step back at this point and to think about sort of software engineering techniques, specifically data-oriented techniques. I actually find it's helpful sort of in modern practices to stay away from classes unless you really need them when you're doing a first draft around. And instead think about specifically what is the static data model, how is it represented in memory? You can see like the zig is showing, right? How is it going to be packed? What sort of aggregation of bytes do you need to define a specific representation? So let's start with, first we know we're going to need a surface. We're just going to basically use this as the buffer for the image data before we pass it off to the GL uniform. We know we're going to need some vector data. So we have a specific vertex format here. And I will explain this in just a moment. Keep in mind this is basically 2D points. So the pixel format is 4 floats per pixel, or vertex rather. You do have to think about your vertex format in GL, and that's fine, that's okay. For given vertex, what attributes does it have? Depending on what your models are and what your pipeline looks like, that might look different. Some vertices may have specific normals, or those normals may be associated with a different index map for the different faces, or you may be computing those on the fly. So some vertices may have UV coordinates. They may have multiple UV coordinates for different maps. There will probably be a position of some kind, etc. So in this case, we have each vertex defined by 4 points, because this is 2D. It has a sort of an XY coordinate, right? And it has a UV coordinate that we're going to use to map the sprite image onto that sampling within the shader. So let's define indices for it. So we have 2 triangles here. The vertices 0, 1, 2 form as a triangle. We're going to use an index member for that. And 0, 2, 3 forms the other triangle. Now we can think about how are we actually going to structure the application. So this is what I was talking about when I think about what data you need, keeping in mind this is very not sophisticated. Well, I can talk about, I wrote an interesting article about sort of evolution of game engines that I might actually put up in here at some point. Let's think about the context of like one structure for the application. What are we going to need for this? Well, we're going to need the window. That is SDL. That's actually going to be a pointer. There's going to be an OpenGL context, also provided by SDL from that window. There's going to be our vertex object, a couple of different GL handles to represent where these are stored in the GPU. Some of these we might not end up using, actually. We will see. And then we're also going to need some handles to represent the texture uniform, the shaders, and the program itself. This actually is enough, this structure is enough to define our application. Yay, isn't that wonderful? So now we want to think about what are we actually going to do with this. We're going to initialize it. Let's just say we have an app here. And of course there's going to be main. And we're probably going to want to free it too. Okay, so we are also going to want some helper functions here. So we're going to want to get the source content of our shaders. We're not using Super or anything in order to build them. And then we'll have some helper methods. Keeping in mind all these things are stored as part of the application structure, so that's really the only thing we're passing around. Material can mean a couple of different things. In this case, it's basically just our shader parameters, including the texture. We're going to have a specific function for the render loop. In more sophisticated applications, you'll actually want multiple functions for different threaded parts of the loop. That may be something we talk about at some point as well. So how are we going to use all of these things? We have them scaffolded here, so we can actually go ahead and define how we're going to use them within the context of the program. So let's say this was a global. We're going to use an SDL image helper function here. I can't remember if that cast is strictly speaking required. Allocate the memory for a structure, and then initialize it. If you've used 3JS at some point, you'll recognize some of the constructs here, particularly with respect to geometries and materials. We don't flesh that out very much in this one, but I might use that in sort of a future sketch of how this evolves into something a little more interesting. I was going to say professional, but I don't know. Professional is the right word. Okay, let's, yep, yep, yep. Get an event loop defined here. And if that is a close event, we will simply break out of our loop. After we check all the events, we're single threaded here, so we will pass it off the rendering. And then, of course, we need to clean up. This is hopefully not too hard to keep track of. I like to think it's easier when I do it this way, but it's an interesting sort of technique for developing at the file level. Is sort of a back and then forth. Starting with dependencies and in global data structures, and in particular structured, type definitions. It's sort of like declaring prototypes for these things, right? And then once you get to the end, it's like, okay, now that I've put, have the pieces declared, let's start using from the top level, and then we can dive into the implementations of each one. We have full context in mind in that case, and defined in the file. We can look at it to see exactly how it's going to be used. So if you're wondering why we're doing it this way, all right, okay. There's something missing here, actually. Free app. Yeah. I can't remember. Deallocate. Okay, I don't think we deallocate in the free function. I could be wrong. We'll see. All right. Okay, so now let's go through, when we initialize the application, what are we talking about? Basically, this is sort of top level outside of any other subsystems in your application. So really, it's just your standard SDL checks. We want to initialize SDL with video support. Make sure that's everything happened okay. Use standard air buffer if it's not to report. I kind of like making sure that this makes sense. Like first part of your error message makes sense if you're just saying what you're doing. What are you doing? You're initializing SDL video and then failed. So if you want to go in later and just debug, you can say something like this, right? What are you doing? Of course, given that, I should probably make sure I actually say use the participant. And then this is a nice way to just sort of quick and dirty break. So what are we doing here? We're initializing SDL with video support. And then SDL is actually going to be used to create our window. SDL being a nice cross-platform library. This would be a super big pain to try and handle if we were, trying to allocate an external window versus a Wayland window versus a Windows window versus, Once you have a window, you can usually get a GL context, although that's not exactly straightforward either. Let's see. Let's make this. I can't remember how big our image was, and we're not doing anything too crazy here. So, GL. All right. Really, that's the important part. Make sure that was allocated. Surprising amount of cross-platform grease just comes from having a capable Windows manager from which you can get a GL context. And that otherwise would be honestly like 80% of the effort if you didn't have that. So yeah, SDL is very nice. Let's define what GL version features we're going to need. Boom. Boom, boom, boom. I messed it up. I messed it up. It's amazing how many typos I make the moment I start streaming. Which isn't to say that my typing is perfect when I'm not, but it's good practice. All right. What other attributes? So, purple masks. We want a double buffer. Yes, please. Just swap it. So, And then now we can get our GL context, STL create context from the window handler. Then once you reach this point where you have a GL context, everything else, you're home free, right? Everything else, you don't need to worry about the wrapping or the platform management, etc. So you have GL context, and we are in C. We can't use single quotes. Make sure we clean up in the event things die. And then glue itself. Actually, we have enough now. We could probably jump over to the CMake real quick. Just make sure we have our build configuration set up before we go through too much of this zany nonsense here. But yeah, let's go ahead and do that. Because this isn't going to change much once we get it configured. Let's take a look at CMake. So we have sort of, standard CMake requirements. CMake minimum version, project 11 SCL, OpenGL. It's going to be outlets, blah, blah, blah. Yeah, sure. Only one source file here. I like putting paths in quotes so you can find them. There are some options. You don't have to do these, but if you don't do them, there's more work. So just in the interest of making sure we're not building anything that requires too much customization here. Good old add subdirectory. So that will recurse into our dependencies, all of which also has CMakes. So we also want to make sure when you include things, it's looking in those paths, which can change from project to project. So we have I think they're all just include folders. Let's check. Include, include, include. Okay, yay for standard folder structures. We don't need to link against these. When in doubt, you can always look at the add library definitions in the CMake for a particular project to figure out exactly what the symbol is. There's also some nice find package helper functions in CMake that might be worth diving into at some point. For now, this is enough. Link it against OpenGL, which it should find from your platform libraries. Against, in this case, we're by default doing the static build of glue, and of course, STL image. So those are basically just the libraries. We're going to use output path. Assuming configurations debug by default, make sure it's built. Because we have some static resources here. Probably worth talking about CPAC at some point, but in the meantime, we want to make sure these static resources are going to be available to the runtime folder. And this is a useful way to do that. We need our vertex shader. And of course we need our actual logo. Oh, and lastly, there are some dynamic resources here. Some of these libraries are going to be DLLs, shared objects. So let's make sure once they're built, they can be copied over. We're cheating a little bit here. We know what they are and where they'll be, and of course where they need to go. And basically the same thing for, I think it's image. See the other DLL? Dun, 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 dun. Yeah. So if we wanted to, we could go ahead and run that build right now. Should we do it? Yeah, let's do it. Oh no, because we'd be calling something, it would still, we wouldn't be able to run it, right? There we go. Okay. Yep. Configure away. Okay, so back to our source. Let's finish initializing. Let's go through the initialization first. So we initialize the application. How are we going to initialize the shaders? So this is shader build process. Define an error buffer to get the error messages if things go wrong. In this case, we're going to, since we only have one global vertex object, set these up here. Okay, so let's compile the vertex shader. First, we need a handle. So, hey, OpenGL, create a shader for me, please. And then give me the idea. ID. By the way, it's a vertex shader. All that means. We know we're going to have some sort of basic get source function here. We're going to tell GL here is the character buffer for this shader that defines the source. And please compile it for us. In modern graphics programming, this would not be part necessarily of the application build process. You'd be packing these in along with your other assets. So you'd be using something like SPIR-V with Vulkan, for example, to do some sort of intermediate representation of the shaders. But in this case, we'll go ahead and compile them at runtime, effectively, is what we're asking GL to do here. Get the results. Assign that integer. And check and see if we done goofed it, which does happen. Dump that log down to our error buffer here. Do some really crazy hacking, null terminate. Don't try this at home, kids. Okay. So basically, we do the same thing. We will go ahead and cheat for the fragment shader. If this is Greek to you, then rest assured, I would love to talk more about GLSL and the pipeline there. There are plenty of other great videos on that, but I love talking about it so much we might as well just do it anyways. Okay, so basically same thing, only this is the source for the fragment shader. Bapadong, air, yep, fragment shader. Yep. Okay. And then once we have those individual programs compiled, we need to link them into a shader program. Hello, OpenGL. Please create a shader program for me and give me the handle. Attach this code that I compiled. Here's the vertex shader. Here's fragment shader. That fragment shader, in this case, has a uniform for the texture data, so we're going to need to get a handle to that location. We'll sign that. Then link it. Should probably check for errors here too. I think we will skip over that for now. Okay, so this is enough to initialize our shader code. Now let's talk about our vertex data. So basically our geometry, right? It's very simple geometry. It's two triangles. Let's do this in an extensible way, though, where we'll be able to reuse this for the next step. So let's get a new buffer. Hey, GL, give me a buffer, please. That is an array buffer, by the way, OpenGL, in case you were wondering. So MVBO now defines the handle to our vertex buffer object. Here is the data. It has this length of data. Notice we just stored it as straightforward vector of, did I misspell that? Squirrel, got distracted. It is capitalized. I'm so smart. So basically, from the beginning address of this, it's all stored in a sequence, right, in memory. And there's going to be 16 values, and we're going to tell it how those values are structured. So static draw. And we have elements of those objects. Not very many. So far, it's good. Yep. So now we can actually bind the data. So this is where the shader program knows, hey, the data that will be available to you is coming from here. These buffers that we've defined. We have an attribute. In this case, we're going to call it XY. The XY attribute for each vertex is the two-dimensional position. Surprise, surprise. Okay, so here's where things get fun. Remember I talked about custom vertex shader formats, or vertex models. Let's see. I'm just writing this out and I'll explain to you what it means. So, given that sequence of data, we need to tell GL how to translate and iterate over that sequence, and specifically how each segment in that sequence maps to the values that our shader programs will be run against. So in this case, what are we saying here? We're saying there's two values. We're saying that each sequence of values is offset by a stride of 4. And those two values for this particular variable are 0 away from the beginning of that sequence. So it might make a little bit more sense if we see that in comparison to the other attribute here, which of course is our UV data. Same sort of thing here, only in this case, we are passing off the texture coordinates. So again, there's 4 values in each sequence. But they are offset from the beginning by 4. So there's 2 values, U and V, right? There's a stride of 4 between each sequence, because each one is 4 long. And within each sequence of 4, the UV values are offset by 2. So if you think about how the vertex data is structured, right, we have X, Y, U, V. That's what we're telling OpenGL is what the format of those vertex attributes are. Why is it still complaining? Argument type void. Did I miss a comma somewhere? GL false. Yep, I did. There we go. Okay. And then we only have 1, so we will just enable this up front here and not worry about swapping it out. So that defines our geometries, and then our materials are basically getting the image data. If you're familiar with GLSL, we are trying to load this into a uniform. So that does not change on the GPU once it's loaded. It's something you can look up at sample, determine the individual pixel color. Texture. It's a 2-dimensional texture with this handle. From PNG, it's going to be RGBA. I believe it's 256 by 256. When in doubt. It must be. Oh, not mean to do that. Edit. Paint. Resize. Oh, seagull. Goodbye, seagull. Alright, I like our seagull. It's random, but he's kind of cute. Alright. Obviously, you could look at that dynamically, look at the surface properties once it's loaded as a STL surface. So you wouldn't need to hard code this. You don't have to enable blending here, except for the background, of course. since it's transparent. This has always been awkward, the way that GL tries to define the blending functions. And then we did this fine sampling parameters. One minus source alpha. Yep, okay. So if you're not looking at it at exact resolution, this defines how it can resample the actual image pixels. So it's 8-bit image, which I believe is the case. And then we get the raw pixel data from our SDL surface. And that's enough. Okay, we are just about done. The rendering loop itself is very straightforward. We're going to clear the color buffer. We'll just use a nice bright red here so we can see exactly what's going on with transparency in case we need to debug blending at first. And in this case, we already have everything loaded because there's only one object, only one set of buffers, only one program. We're going to draw 6 entries. So grouped into 3, those will be triangles. And then most importantly, swap the window with this to our Windows context. I have definitely forgotten that and wasted lots and lots of time trying to figure out why nothing's showing up. We're just about done here, believe it or not. We just have a few helper functions we need to define here. Loading the contents of a file. Make sure we can read it. Read it into a buffer. Get the contents of that buffer and cast it into the format that GL is going to need. Which, of course, is a C string. You can never escape the C strings. But you can still use an integrator. Maybe for standard copy. Size, null terminated, and return our buffer. Lastly, just sort of our general cleanup. We will unload the graphics program, disable our arrays, detach all of our shader information, Delete the actual program from the GPU, as well as the constituent shaders. Our texture handle also needs to be deleted. Our buffer objects need to be deleted. And our vertex arrays need to be deleted. And lastly, there's the other SDL cleanup. Go in reverse order. Always a good idea from how we initialized it. All right. Why you're pretending like you're not a thing. Did I misspell something? GL delete textures? GL delete textures? No. I'm going to put that up to a Visual C or VS Code quirk. Okay, so we're not quite done yet. We're done with the C. We have very basic shader code here. In this case, we have not ints, vectors for the position, of course, or attributes. Going to interpolate UV coordinates. And then our position, we're going to put into 4D space here. Don't ask why it's not 3D. That's probably another video topic. So the position, we're not doing any crazy transforms here. We're just trying to show something on screen. It's just the XY coordinates, and then we're going to treat the UV coordinates as a varying so we can interpolate them to get the right pixel location. And for the fragment shader, it's even more straightforward. Our varying that we computed. We'll need our uniform, of course. And the output of this pass will be the color of the pixel because it's a fragment shader. That will be sampled from our texture data, and that should do it. Okay, moment of truth, ready? I misnamed it. Let's look at the build target here. Got the right version, right? STL2, 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 STL2 main. That should be, oh, yep. Let's try that again. This might take a while now. Okay, building SDL, yep, thank you. Thank goodness C compiles so quickly. Let's open up our build artifacts here while we wait. So you can watch it populate. You can see it copied over the static resources already. It's building SDL image and continuing to build SDL. But you can see our exe actually showed up there already, which is nice. Okay. Now it's doing the tests. I don't know if we need the tests. Probably could have disabled that. Let's give it a shot. What do you think? Not bad. Not bad. So let's step back for a moment because I started this conversation off by saying, well, that's actually really easy to get started with. OpenGL. That took a little bit of time, didn't it? But if you think about what we were doing, none of these things are really optional, even whether you're using OpenGL or anything else. Most importantly, we've put ourselves in a position here where it's fairly extensible to more sophisticated things we might want to do. But out of the box, even to some optional dependencies like STL image and defining our own custom shaders, like we were able to get something going pretty well. It's pretty well organized. We have a basic structure for the application. It'll be really easy to break this off, break this apart. Let's see, sort of big takeaways here. The first is with a little bit of help, like you can get started with this like a sprite-based application very easily, and you can do it in a way where you can actually make it possible to do a lot more in the future after that. Second is, believe it or not, so Winston Churchill had a saying like democracy is the worst form of government except for all other form of governments that have been tried. OpenGL is like going back to the original point of reaction or comment, like, yeah, it's the worst way to get started on it, except for everything else. Compared to GDI, compared to Cocoa, compared to Carbon, compared to Wayland, compared to Vulkan, compared to like this is so much more straightforward. Everything here has a reason. You know exactly what it's doing, and you want to be able to control what's going on. So it is a little bit involved, but at least to me, maybe it's just because I've stared at this too much over the years, but like this actually makes sense. Compared to some of the more obscure setups, you're not trying to abstract away too much of like what's going on in the GPU. You have a nicely customized graphics pipeline, but you still have a lot of control over it, and it's still fairly straightforward to set up and get something going. This is sort of part one of two. In part two, I'm thinking of looking at sort of a basic 2D engine that you might put together based off of this. But this is enough to get going. And this is actually one of the easier ways to start doing like really quick, low-level 2D cross-platform applications, especially if they're sprite-based. Take care.